Hi guys, so let's talk about section 11.1 part 2. So in 11.1 part 1 we discussed kind of tiptoeing around actually performing a hypothesis test for goodness of fit, a chi-squared goodness of fit test. But we went over the conceptual part of that, what that really is supposed to do. So in this note sheet we'll just do 2 hypothesis tests. That's about it. Okay? So carrying out a test, of course, you know this, before you build the confidence interval, before you do a hypothesis test, you check for conditions. If the conditions are met, then you can do it. Okay, so in other words, be a responsible user of statistics, not a foolish one, like many people are. So here conditions are random. The data come from a well-designed random sample or randomized experiment. Check 10% condition when sampling. So if you are taking a sample, then check the 10% condition and large counts condition. So now we have 3 conditions for distribution shapes. Large counts for confidence interval and hypothesis test for proportions is large counts, which is NP and 1 minus P must be greater or equals to 10. We have central limit theorem for means. Confidence interval or hypothesis test of means, we've got central limit theorem to tell me that the sampling distribution of the sample mean is approximately normal. And then here we have the large counts condition for chi-square goodness of fit is all expected counts are at least 5. Expected counts. So not observed counts, expected counts. Okay? Then if that happens, the sampling distribution of the chi-square statistic will be approximately a chi-square distribution. That's what this says. So what I would do if I were you, just write the condition is met, not to get yourself confused or maybe write the wrong thing down. Okay, then the chi-square test for goodness of fit. Suppose the conditions are met to determine whether a categorical variable has a specified distribution in the population of interest. Expressed as a proportion of individuals falling into each possible category. Oof. That's a lot of wording. Okay, that's a lot of wording. So, to determine whether a categorical variable has a specified distribution in the population of interest, expressed as the proportion of individuals falling into each possible category. So, going back to our M&Ms thing, categorical variable was color. Population of interest was all M&Ms, how they're distributed, according to how many % of each color are in each category. Okay? In other words, what's a percentage of each color? So category for us was the color names, so blue, etc. And we wanted to know what proportion. They made a claim about a proportion, and we tested that claim. Okay? So, any case, I hope you get the concept. Doing the test itself is not too bad, but the concept is important. All right, so the stated distribution of categorical variable in population is correct. That's your null hypothesis, and it's not correct. That's your alternative hypothesis. You can say it this way, or you can say it by listing the actual proportions. So the other one we had was null hypothesis is proportion 1 is this, proportion 2 is something else, and so on. Or the alternative hypothesis is at least 1 P sub I is incorrect. Okay? That was the other way of doing it. So there's 2 ways of stating hypotheses. Then start by finding the expected count for each category. That's what we did together. Find the expected count and then calculate chi-square statistic. There's the chi-square statistic. Remember, this is on the formula sheet. Life is good there. Okay. And then use your chi-square statistic to find the p-value. And the degrees of freedom for chi-square is the number of categories minus 1. You must state all that. All right. So, just remember, chi-square statistic compares observed and expected counts. Don't work with proportions. So don't write down proportions Don't put proportions in your formula. It's not proportions, it's counts, okay? So that would be wrong. And then the other one is, when checking this, also we're talking about expected counts. Expected counts. So when checking this condition, we're talking about expected counts, not what I observed. Okay? All right, so there's that. Let's do one. Let's do a chi-square test for goodness of fit. So think again how this works. I drew this picture for you last time. Here's my population. Okay, whatever the population is, then I have a categorical variable, and the categorical variable has certain categories. Okay, so category 1, category 2, category 3, etc. And what we're trying to see is the claimed distribution of the categories in the population, whatever it is, some percentage or proportion, is that claimed distribution correct based on the sample data that I gathered. Okay, so that's single population, single sample, and we're trying to see if my categorical variable is distributed as claimed across that population, which means I will check it for my sample as well, okay, by calculating the expected counts. All right, so that's the overall picture there. So are births evenly distributed across the days of the week? All right. Okay, the one-way table below shows the distribution of births across the days of the week in a random sample of 140 births from local records in a large city. Okay. So you should be able to at least tell yourself what's the population. The population is births in a large city, okay? And I took a sample of 140 of them. And I want to see if they're distributed evenly. So this is maybe a bit easier, I think, than our M&M one, because distributed evenly means each day has the same proportion of births. So if the whole proportion of births is 1 or 100%, then each day should have 1/7 of that 1, or 1/7 of 100%, because there's 7 days. Okay? So that should be going on in your mind. Do these data give significant evidence that local births are not equally likely on all days of the week? Use your calculator to calculate a test after doing it by hand. Okay. So do we have enough evidence for the alternative hypothesis, is what this is asking, okay? Or can I not reject the null hypothesis? So let's say state we will perform a test of, let's write our hypotheses. Null hypothesis is birthdays are evenly distributed across days of the week. Okay? Are evenly or evenly distributed across the days of the week in this large city. Okay, and the alternative hypothesis is birthdays are not evenly distributed across Okay, so please don't do that on your test or in your work. Write it out, but I'm trying to keep this video short, all right, which is not going to happen in any case. The alternative way to do this, or you can do this. The null hypothesis is P sub Sunday, P sub Monday equals P sub Tuesday equals equals P sub Saturday. Okay, and that's all equal to 1/7. All right? So that each proportion of births for each day is 1/7. Okay? And then the alternative hypothesis is at least one P sub day is not equal to 1/7. Okay? And then you have to define, see, since I did this, I have to define it. So, and since I did this, I have to define it. So where P sub day is the proportion of birth on the specified day in a large city. Okay? The proportion of births on a specified day in this large city. Okay. So you can do whatever you want with that. Okay, pick one. I am going to, for now, let me erase this so I have more space to do the rest of the test. Okay? Pick the way that you want to do it and go for it. All right? So I'm going to leave it at this. And then it's say, okay, we did this. And then also, please always state your significance level. Let the significance level be 0.05. All right. Then plan. And you have to name your procedure. Okay? If all conditions, or if conditions are met, we will perform a chi-squared test for goodness of fit. Or, let me write it this way. A chi-square goodness of fit test. Okay, so here's the procedure name. Ooh, different color. Here's the procedure name. Chi-square goodness of fit test. Okay, and just think about goodness of fit test. How good does the population distribution fit the claim, kind of a thing. That's what you have to think about. All right, that's why we call it that. All right, so again, random is always of utmost important. The sample is a random sample of 140 births. Okay, the sample is a random sample of 140 births. All right, good. And then independent, and actually usually what we do is large size next, but I'll do independence. So what can I say about independence here? It's reasonable to assume that births are independent of each other. So me being born on a Sunday doesn't affect you being born on a Monday. So let's say it's reasonable to assume that individual births are independent of each other and that there are more than in a large city, I need to beat 1,400, okay? That there are more than 1,400 births in a large city. The 10% condition is met. I'll say is also met, okay? All right, and then large counts. check the large counts condition. Or sorry, we're not calling it large counts. What are we calling it here? Oh, it is large counts. Good. Okay, large expected counts, right? Not observed. Large expected counts. Okay, large counts condition. So now I have to calculate all the expected counts. But this is not too bad because all I have to do, they're all the same. Okay. Remember, an expected count is the proportion times the sample size. The claimed proportion times the sample size. Okay. So my expected count here would be the claimed proportion times the sample size. And that would be 20. Okay. So we say all expected counts are 20. Okay, so the let's do it this way. Okay, all expected counts are 20, which is at least 5. Okay, showing that you know the condition, which is at least 5. So the large counts condition is met. All right. So now we can do it. Say do step, and we write down our formula, which is on our formula sheet. Chi-squared is observed minus expected squared all over expected. Okay, and we can actually fill that in. So now we fill stuff in. So what I have is, oh, sorry, and it's the sum of that. It's not just one set, it's the sum of all of the observed minus expected squared divided by expected. Okay, so we can fill that in. We take my first observed, which is 13, minus my expected count, which we said is 20, okay, squared all over expected. And this is actually very simple because all the expected counts are the same. So then I do 23 minus 20 squared over 20 plus. And what you can do is, if you have a chi-square test and you have to write all this stuff out, just do this, all right? And then do the last one maybe. Okay, so use some ellipses there to show that, hey, I know how to substitute in the formula, but I'm not stupid enough to go and substitute every number in the formula. 15 minus 20 squared over 20. Now, let's see what happens. Equals. Okay, and you should just get the statistic from this. So we should go do this in our calculator and see what we get. Okay, so you do the test in your calculator, and I'll have to make a separate video for you about how to do this test in your calculator. But let me say, you can, if you calculate these components, you should at least do that. And I think your calculator will show you that, but I'll show you that in the video, okay? But then you can list out your, what we call components or contributions to the chi-square statistic. And we'll talk about this a little bit more. And then what you get is 7.6. All right, that's your chi-square statistic. And then what you have to do is say, all right, now I want to calculate my p-value. What is the probability that I get a chi-square statistic that is greater or equal to 7.6? Okay, and if you do that calculation, you get 0.269. Remember, you must list your degrees of freedom, and in this case there are 7 days of the week, okay? So 7 minus 1, which is 6. That is my degrees of freedom. And then now we have our answer. Our p-value is quite high. So we can write our conclusion. Since our p-value, which is 0.269, is greater or equals to alpha, which is 0.05, okay, we fail to reject the null hypothesis. Okay. We do not have sufficient evidence to conclude that, what was our alternative hypothesis? The birthdays are not evenly distributed. It's a double negative, but okay. That the birthdays are not evenly distributed. Okay. Across the days of the week in this large city. In this large city. So I can't say that it's not 1/7 the distribution of births across days of the week. All right? Okay, guys, so let's see. I will make you a calculator tutorial of this. Basically, what it involves is going into list 1 and entering your observed, going into list 2 and entering your expected. And this is definitely not our hypothesis test, degrees of freedom 3. For us, we would have degrees of freedom 6. And then you would get a chi-square statistic. You get your p-value, and the nice thing is you get your contributions. So all of these numbers, at least for a goodness of fit test, okay? So all of these numbers, the contributions, or sometimes called components, that you would need to write down here are also given to you, at least for a chi-square goodness of fit test, right? I don't think they are given to you for one of the other tests. In any case, we'll see that when we get there. All right, so I think what I'll do is just make you a quick calculator tutorial about how to do the test on your calculator as well, just so that you're not confused. Okay, you can watch that right after this. So what I'll do is let me stop the video here, and then I'll make another video for the second hypothesis test example, which is example 2. Okay.